Hello students. So in the previous class we started with a series solution for ordinary differential equation. We were mostly looking at second order ordinary differential equation. We learnt about what's ordinary point, singular point, regular singular point, irregular singular points, and we also worked out, or we learnt a method if you have an ordinary point and if you are looking for a solution near it, then in that case how do we calculate the series solution. So, that we saw that you can substitute something like yn equals to, or y is equals to, we can substitute somewhat this, and then you put it into the equation, equate the coefficients, determine an, and that will be your series solution. So, this is fairly simple if you have an ordinary point, but if you have a singular point, then as I mentioned that you can substitute y is equals to x to the power rho into summation n from 0 to infinity a n x n. There is a reason that why we considered this kind of expression, and since today I have a complete class, I will be able to derive that expression. So, in the previous class we did work out one example. So, now with this theory you can be able to connect with that example, right. So, I will dedicate this entire lecture just to derivation of the method, something called Frobenius method, when you have a singular point. It is very how to say intricate, and it is little bit lengthy. So, we will cover maybe one or two particular cases, but the entire theory you can look into the textbooks that I have mentioned. It's just that the derivation is too lengthy. So, the idea I will share, and for the derivation you can look into the book. So, let us say that we do have a singular point, right. We have a singular point, and now we have to find out a series solution near that point. So, then what will happen? Suppose let us take one example, x square y double dash x plus y equals to 0, right. So, obviously x equals to 0 is the singular point, of, let us call this as equation 1 of equation 1, obviously. And suppose you want to go with this traditional method, that is y equals to summation n running from 0 to infinity a n x n. We want to go via this method. So, obviously we can substitute y double dash equals to x square summation n running from 0 to infinity a n, then n into n minus 1 x to the power n minus 2 plus summation n running from 0 to infinity a n x n, x to the power n. So, this equals to 0. So, we can multiply by x square inside, and this will become summation n running from 0 to infinity a n n times n minus 1 x to the power n plus summation n running from 0 to infinity a n x to the power n. So, basically what will happen is we will take n from 0 to infinity n minus 1 plus 1, and then we have x n a n x to the power n equals to 0, which shows that, I mean for n equals to 0. So, if we substitute n equals to 0, then this will give. So, for n equals to 0, we will get n equals to 0, that means I will get a 1. So, n equals to 1, 0, 1, 2, 3 and so on. I will get a n equals to 0, because what will happen is here we can say that x to the power, this is a general expression, and if this is a solution, then the left hand side must be 0. So, basically this n into n minus 1 plus 1 into a n, that has to be 0, and therefore, for n equals to 0, 1, 2, 3 and all that, all the coefficients a n is becoming 0. So, for values of n equals to 0, for 1, 2, 3 and so on, a n is equals to 0, and hence the trivial solution is the only solution as per this method, that means there is no series, of the form y is equals to summation n running from 0 to infinity a n x to the power n, which may be the solution, which is the of the form this, which is the solution of 1. So, this tells us that if you if we consider of the series only this type, then in that case we may not be able to get the series solution, right. So, technically this method actually fails if you go by taking only this type of series, but that is not true. I mean, we can get a series solution, it is just that taking only this will not help, right, because if you take this, then all the coefficients a n will simply become 0, right. So, now then what will happen? How do we recover this? How do we save this? So, then what we will do? We will take the general case. Let us take the general case. We have P0 x into y double dash, P1 x into y dash plus P2 x into y equals to 0. Let us call this as equation number 1, where Pi's are polynomials. So, obviously, if this has a singularity, let us say at x equals to x0, this is the singular point. So, proceeding like previously will not help, we will not get any solution, any series solution, sorry. So, then we will adopt a method, that is writing the solution as y equals to x to the power rho into that infinite series. So, we are going to take help what is called Frobenius, B-E-N-I-O, N-I, let me write it again, Frobenius method, right. So, we will take help of this method. Okay. So, what does this say? So, we will start with same equation and we will multiply by x square on both sides. Since it is a second order, we want to multiply by x square. So, this will become x square P0 x y double dash plus x square P1 x plus P1 x y dash plus x square P2 x into y equals to 0. Now, let us divide both sides by P0 x just to make it a rational function in a way. So, this will become x square y double dash plus x p x into x y dash plus x square q x. So, we have divided both sides by P0 x. Okay. So, now let us call this as equation number 2. So, obviously, x into capital P x and x square into capital Q x are regular at x equals to 0, right. They are both regular at x equals to 0. So, we can put x p x as p0 plus small p0 small p1 x into x plus small p2 into small p2 into x square plus dot dot and so on ps into xs plus dot dot and so on. This is equation number 3a, and similarly x square q x I can write as q0 plus q1 x dot dot and so on qs x to the power s dot dot and so on. This is a theory, so I hope that you have patience to see the derivation, because it will be a little bit long. Okay. So, now from this relation, from relation number 2, for the solution of 2, we put y equals to x to the power rho C0 plus C1x plus C2x square plus dot dot up to Cn x to the power n plus dot dot and so on. That is the infinite series we want to consider. And if we multiply, then this will simply become C0 x to the power rho plus C1 x to the power rho plus 1 plus dot dot and so on Cn x to the power n plus rho plus dot dot and so on. Let us call this as relation number 4. So, now we can calculate dy dx to put here and d square y by dx square to put here. So, if we put all those things there, then what will happen, and then we will put for x px and x square qx. So, it will be a rather lengthy expression. I am going to write very few terms. So, substituting for x px, x square qx, y double dash x, y dash x and y in equation, I believe it is 2. So, then what will happen? We will get C0 rho into rho minus 1 x to the power rho plus C1 rho plus 1 rho into x to the power rho minus 1 plus dot dot and so on. We will have Cn rho plus n minus 1 x to the power rho plus n plus dot dot and so on. Then we have that x into px expression. So, that is basically small p0 plus p1x plus dot dot and so on ps xs plus dot dot and so on. Similarly, we will have expression for y dash x. So, now this will be multiplied by y dash x, whatever we will get here C0 rho x to the power rho plus x to the power rho plus C1 rho plus 1 and so on. So, there will be a lot of terms actually. So, similarly, we will have all the other terms here. Okay. And also we note that C0 is not equals to 0. So, here wherever we have this expression, here we might as well mention C0 is not equals to 0. Okay. All right. So, let us proceed. So, this is equation number 5. We have to put all the values that means px, xpx, x square qx, y double dash x, y dash x, yx, and then multiply by all those x and x square and so on, x into dy dx. So, we have to multiply dy dx by x. So, you put all those values and you will end up getting a very big expression here. Now, the coefficient of x to the power rho, the coefficient of x to the power rho in equation 5 is C0 into rho minus 1. You have to just believe me that this calculation should be correct. So, C0 rho 0 into rho and P0 into rho, not rho 0, P0 into rho and plus C0 Q0, right, and that of x to the power rho plus 1, that of x to the power rho plus 1 in 5 is C1 rho plus 1 into rho plus C1 P0 rho plus 1 plus C0 P1 into rho plus C1 Q0 plus C0 Q1. Similarly, the coefficient of x to the power rho plus n, similarly the coefficient of x to the power rho plus n in 5 is Cn rho plus n into rho plus n minus 1 plus summation s running from 0 to infinity c of n minus s ps rho plus n minus s plus qs, right. So, these are the required coefficients where C0 is non-zero. As you can see how lengthy it is getting, and we are not done yet, we are just halfway. Okay. So, therefore, from equation number 1, 2 and 3. So, equation number 1 is this one, where is that? Equation number 1 is, so basically we are referring this as let us say, where is that? So, this as equation number 2, and equation number 1 we can call it 1, that one. So, 1, 2 and 5, what do we basically get? We will get, let us go to next page. So, from now we will just collect the terms. Equation 1, 2 and 5, we obtain, what do we obtain? We will obtain d square y by dx square plus capital Px into y dash plus capital Qx into y is equals to C0 rho times rho minus 1 plus rho into P0 plus Q0 x to the power rho minus 2 plus C1 into rho plus 1 into rho plus rho plus 1 into P0 plus Q0 plus C0 rho into P1 plus Q1, and this bracket, so there is a bracket here Q0, and then this whole bracket into x to the power rho minus 1 plus dot dot and so on. There will be many more terms, right. So, therefore, the solution or the equation 4, will be a solution, or the 4 basically, do not write any term, the 4 will be a solution of equation 1 if the coefficients of each term containing similar powers of x on the right hand side, of, let us say this is equation 6 of 6 is 0, right. So, therefore, the coefficient thus the equating the coefficient of x to the power rho minus 1, thus equating the coefficient of x to the power rho minus 1 from 6. What do we get? We will get C1 rho plus 1 into rho plus rho plus 1 into P0 plus Q1 plus C0 rho P1 plus Q1 equals to 0. So, from here we will get, so this gives C1 by C0 a function of rho, that means F1 rho, say. Similarly, we will equate the coefficient of x to the power rho. So, if we equate the coefficient of x to the power rho to 0, we shall get C2 in terms of C1. So, similarly, equating the coefficient of x to the power rho from both sides of equation number 6, from both sides of equation number 6, then we shall get C2. We shall get C2 in terms of C1, in terms of C1 and C0, and hence in terms of C0 only, so that C2 by C0 is equals to F2 rho and so on, right. So, like that. So, in the same way, if we equate the coefficient of x to the power rho plus n minus 2, then we get the coefficient of Cn, right. So, we are equating the coefficient of x to the power rho minus 1, rho minus 2 dot dot up to rho plus n minus 2. So, if we equate up to that exponent x to the power rho plus n minus 2, then we will get the equation for Cn, right. So, in this case, in the similar way, equating the coefficient of x to the power rho plus n minus 2 to 0, we get the equation for Cn, the equation for Cn. So, therefore, what will happen is, thus equating the coefficient of all powers of x on the right hand side other than x to the power rho minus 2 to 0, thus equating the coefficients of all powers of x to 0, all powers of x on the right hand side other than to 0 other than x to the power rho minus 2, we get d square y by dx square plus px into y dash x plus qx into y equals to C0 rho times rho minus 1 plus rho times P0 plus Q0 into x to the power rho minus 2, right. So, this is equation number 7. So, therefore, this is equation number 7. Therefore, thus the solution y is obtained as y equals to C0 x to the power rho 1 plus C1 by C0 x plus C2 by C0 x square plus dot dot and so on, Cn by C0, everywhere we are getting C0, Cn by C0 x to the power n and so on. So, basically C1 by C0 is our F1 rho p. So, this can be further written as C1 C0 x0 is 1 plus x F1 rho plus x square F2 rho plus dot dot and so on. So, in order to give, in order that the given equation is satisfied by 4. So, that means the equation number 4 where we had y is equals to x to the power rho and all that. So, the given equation 1 has a solution of type equation number 4. Then we have from equation number 7. So, the function y can be solution of equation 1 if rho square plus P0 minus 1 into rho plus Q0 equals to 0, since C0 is not equals to 0, right. P0 minus 1 rho into plus Q0 equals to 0, since rho is C0 is not equals to 0. Now, from here we will solve for rho, right. So, this is not so easy. So, from here we will solve for rho. Now, we will look whether the roots are distinct, whether the roots are same, and whether they are distinct, but differ by an integer, right. So, depending upon what type of criteria that is we are getting, we can be able to write down the solution accordingly, right. And yeah, this is what we were doing yesterday in the example. So, we found out the polynomial for or the function this equation for rho, and based on which we determine what will be our x to the power rho factor when we are considering that series solution, right. Now, if from here 3 cases that I said may arise. So, first one is the given equation, the equation must have a distinct root not differing by an integer. So, 3 cases will arise, we can write 3 cases will arise. First one is may have distinct roots, not differ by any constant, differ by any integer, sorry, not differing by any integer, not constant but integer. And second one is may have equal roots, and then there is a third property, the roots are distinct, the roots are distinct but differ by an integer. Right. So, based on these 3 cases, the third one is very lengthy. If I want to calculate, then it will become further lengthy, but first and second may be simpler, right. So, we will start from this point number 1 and point number 2 in the next class, and we will try to complete this theory, and then we will look into one example, or we will look into the previous example that we started last time, and we will see what we were actually doing, whether the roots were from this quadratic equation, whether the roots were distinct or whether the roots were equal, and based on which what method we have adopted, right. But definitely first and second case is interesting, the third one is a little bit lengthy. So, we will skip that one, but we will cover the first and second method, or first and second cases when